introduction, defining what mechanical transduction and mechanical therapy is. Are people familiar with those two terms? No? Great. All right. Hopefully we can learn as we go then. All right, components and mechanisms of mechanical transduction. So I'm going to break this down into one, the anatomy, which is like your structure, and then we're also going to talk about the adaptability of this and how that influences the shoulder complex and the intertwined tissues. Clinical implication, and then so we're going to dive a little bit deep, and then we're going to come back out of it and try and make it clinically applicable and what that actually means, rather than just sticking within the theory. So I'm big on quotes, and this is one of my favorite, and I think it applies really pertinently to what we're about to discuss. So when any real progress is made, we unlearn and then learn anew what we thought we knew before, right? So when we were 10 or 12 years old, we thought we knew what a squat was. You go through DPT school, you break it down into its components, it gets very complex, like what are the joint moments, and then by this time you've kind of built it back up in your mind and reconceptualized it, would be an example. And I'm about to do that same, and take you through a journey that I went through in understanding how we actually adapt tissues as therapists. So it was 3 to 5 years into my career, and I was feeling pretty confident in my clinical practice. And I started to ask further fundamental questions and asking, like, what are the mechanisms by what we actually do? Because my fear was that I'd get to the end of my career spending, I don't know, several decades worth of treatment and not really understanding the fundamental means by which I actually influence change. And so, you know, we do a lot of things. We influence joint mobility, we provide strength, movement, training patterns, endurance, we do improve people's quality of life, we provide them a lot of education that we often don't get reimbursed for at times, we give them balance, improve flexibility, so on and so forth. And on a high level scale, these are what people would describe us to do, and this is what our job descriptions actually relate. But I had a conversation with a good friend, colleague, and mentor. He went through DPT school with me. He became disenchanted with the profession very quickly. Within 2 years, he transitioned to an orthopedic surgeon PA, and has left the profession. And so but in that, before he did, and in the process of doing so, we've had some conversations. And the questions I would ask him were like, what are the physiological rationales for the interventions that we actually provide? Regarding physiological adaptations, is there more to our interventions than on these system levels, grossly flexibility or strength or stretching or retraining or balance? And his comments were, as therapists, we simply just, again, I used it in the last slide as well, but a quote directly from him is like, I don't know how much impact we actually do. There's like this regression to the mean where people come in, we give them a sense of autonomy and agency with TheraBands and exercises, tell them to go home and do it. And maybe there's just a natural history progression where they're eventually going to get better on their own, or there's a regression to the mean at 5 years, regardless of what exercises they did when they saw you, that they may be plus or minus close to their overall outcome that they would have otherwise achieved otherwise. A very relatively pessimistic viewpoint, but I struggled to give him a counter argument until I had to do some additional research and come back to him. Eventually, everyone is going to have that regression to the mean, was his comment. And so, if we look at the fundamental means by which, and the mechanisms by which we actually improve change, and one of the things I'm passionate about is assessment because it helps me to overcome this underlying bias that we've actually induced improvements, right? Improvements that wouldn't otherwise have transpired if they hadn't been to physical therapy in the first place. So a new definition for your glossary and for your dictionary is mechanical transduction. And this is the process by which cells convert a variety of physiological mechanisms and loading into biomechanical responses and thus adaptations. And it requires grossly 3 steps. So you have the mechanical stimulus, which then induces tissue forces, which incorporates into your DNA, and what they terminology is epigenetics, where our body transforms based off the experiences that we live and the environments that we encounter within our life. And then there's a molecular response, they call it the effector response, that then goes back, influences the tissue, and then prepares it for what is the next otherwise stimulus. So you have the mechanical coupling, the cell-to-cell communication, and then the effector response. Grossly, you can think of it, if you wanted to make it even more simple, is that you have the mechanical trigger, the transmission of the message across the tissues, and then the response to at the cellular level to induce adaptation. Now, we are predominantly responsible for the first cascade in that series, the mechanical trigger, and determining what forces we induce to the biological system. Which is kind of cool, because we are really the artist that determines the epigenetics that then influences the tissue adaptation that people undergo. And so there's a variety of different forces that our bodies and our cells are sensitive to. Everything from tension and shear and vibration, compression, hydrostatic pressures that's within the cell, and even fluid shear. And so there's a variety or a mix of how we can go about influencing the biology. And so when you look at the very basic undifferentiated mesenchymal stem cell, right, stem cells are regulated by cell intrinsic and extrinsic forces that develop. So the externally applied mechanical forces that these cells are exposed to determine what cells they become. And beyond just those that are endogenous within the organism, or those that are now with biological therapies now injected, we are well positioned, and I would say the best positioned, to determine what those cells and how they're otherwise influenced, and what their overall terminal determination is. And then, so you get your chondroblast into osteoblast, tenoblast, and so on. And that would eventually, on a tissue level, determine whether it becomes cartilage, bone, tendon, irregular connective tissue. Again, my intent is not to provide what is redundant biological lessons that we all, I think, are familiar with, but I think it's important that we think about it at this level, because we haven't, for me, it's been a while since I've revisited this, and I think it's actually more and more pertinent, especially as biologics become more available. But again, even to the endogenous, those cells that are already in the system, because every 5 years, every cell in our body turns over. The stimulus that we're continuing to feed it, that is our own bodies as well as the patients, determine like what their structure will actually become in the future. And let's talk about beyond the musculoskeletal system. So if you start to look at mechanical transduction, it has influences in almost every adaptation that you can think of. Even me communicating to you is through mechanical transduction, as the bones rattle within your inner ear is then translated into a chemical signal that your brain then interprets. Right? The only other things that I can think of as examples that aren't that are those that would be chemically induced, such as like iontophoresis or something of the like. But everything else that manual therapy, shockwave therapy, it does fascial manipulation you were talking about, right? It's all induced through some form of mechanical coupling. And that it doesn't end at the musculoskeletal system, it even gets into the neurological system. They're looking at this now in headaches, glaucoma, Alzheimer's disease, even certain types of cancers are determined and treated now through the mechanisms of mechanical transduction. And I also find a lot of the underlying principles that we see within the animal kingdom, also we can learn from that of the biological system. So plants seem to be a little bit more passive, but the reality is situation is that they also rely on mechanical transduction. What you're looking at is a time-lapse accelerated video of Morning Glory Vine as it goes through. Essentially, it's called mastic movements. What you're seeing, and as they go ahead and get the mechanical sensation of touching the external surface, which is known as thigotropic responses and tropism induced by touch, that it actually grows and determines in the actual structure that the vine otherwise would take on. And even on the smallest of biological systems in organelles, one of the litmus tests that I determine whether something is good for my health or not is how it influences my mitochondria, right? And mitochondrial health is also significantly determined by what is mechanical transduction. If you look at the positive influences that are within the cellular organelles. So that is the purpose of that first section was an introduction of definitions of what is mechanical transduction, what is mechanical therapy. Mechanical therapy is the deliberate application of mechanical forces to actually induce a therapeutic response within a biological system that is your patient, or perhaps even yourself. So let's talk about now the components of the biological system that allows the transmission of those forces that we just discussed. So we'll talk a little bit about anatomy and physiology here. Another quote, we want to learn avidly, question repeatedly what we have learned, and analyze it carefully, and then put what you have learned into practice intelligently. Now, if I had to sum up this weekend, it would be this. All right, so there's three key perspectives that we're going to touch upon. We're going to touch upon the bioconsegrity model of human biology. We're going to talk a little bit about physics, which is the laws of thermodynamics, because it's the actual mechanism by which we adapt. I live with an engineer right now. He works for Meta, and he's incredibly intelligent. What I appreciate most is how he's able to boil down things that I take for granted into its most fundamental parts, right? And that is, I think that the better we can break them down to the more fundamental level that we can break things down and then build it back up, the better we actually understand it. And I'm hoping that it's been, so I'll just say from my own perspective, it's been extremely influential in my clinical practice, and I'm hopeful to convey this message to you, and so you can also grasp the importance of it. And then finally, we're going to talk about how that actually influences the adaptation and via the mechanical stimulus. So, bioconsegrity model, let's dive into a little bit of anatomy. So if you think about the classical and traditional perspective of human biology, everything that I was taught in my undergraduate as well as my DPT, I now look at it as somewhat of a reductionist approach. Now, maybe that's by design because it allows for me to feel comfortable with the information, grasp it at a more easily grasp it at a more larger scale means. But then we have to, if we actually look at human biology, it's much more complex than what they told me in my anatomy book and what my professors also convey. So the traditional model, most popular description of human anatomy, describes and presents the skeletal muscles as structural independent actuators with distinct origins and insertions, right? So if we stick with our example of the shoulder, let's talk about the bicep, right? The bicep has two heads. One goes to my coracoid, the other one goes to and inserts intra-articularly within the actual labrum, and then it also inserts onto my radius and my ulna, right? And the bicep does this, and only that is been what I've been told. And I had to remember what the actions were and what the osseous footprints were on the bones and what they were called. Maybe you also had to do the same. And it also uses this classic lever. I also had to know what type of lever the bicep was, whether it was a type 1 or class 1, class 2, class 3. And it presents human biology and anatomy in, as I alluded to, in what I consider now to be a reductionist approach. The anatomical textbook generally organizes things into hierarchical systems of larger important structures at the top, followed by smaller and lesser ones at the bottom. An example of this is that I didn't really, we knew what fascia was, but in my anatomy dissection, I really just kind of schlepped that away. It wasn't that important at the time. I really needed to get down to the larger, more hierarchical, important biceps tendon, shoulder complex, where was the bursa, so on and so forth. And it describes these, in the historical model, these are described as packing tissues, right? It's just connective tissue. You need to get down to like what is the quote unquote meat of the anatomical dissection. And so human biology is accurately more described with a structure known as a biotensegrity model. I'll play this as it goes. So, because I think it gives a great visual of what I'm trying to convey. So biotensegrity is an architectural system that maintains itself through separation of tension and compression. It's a compression of struts, rigid elements, i.e. said humerus or bones, surrounded by stabilizing cables, elastic components, not just muscles, the actual fascial linkages, as we will see. It's not only, it's intertwined intramuscularly all the way down into the cytoskeleton of the cells. The tensegrity systems are super strength. They're energy conserving. They are lightweight relative to the mass that they take up, and they are also resilient in the effect of the damaging forces, right? They are able to accommodate to the forces that are internally and externally applied, and this in itself allows them to be what is known as stress stable. They have internal stability through the balance of compression and tension. And when you look at biological systems, they act more like these biotensegrity models rather than the very linear class 1, class 2 levers that I described in the previous slide. To further kind of draw home point, so let's talk about some mechanical properties and then look at what the biological systems actually have within these properties. So stress and strain curves. Biological systems have nonlinear stress and strain curves, as you've seen like on the toe edge and the plastic bit of a stress strain of a tendon, for instance, right? It's got that kind of upward like slide. I'm thinking, in my mind, I see it as a slide on a childhood playground of sorts, right? And then you have stress distribution, it's global. Structural distribution is continuous. The gravity is gravity independent, meaning like when you actually get down to a cellular level, the cell is, because of the infrastructure within it, it's not really necessarily influenced from gravity. You took a cell and you turn it upside down or this or that. The elements within don't just fall to the bottom of the cytoskeleton, right? And then directional stability is omnidirectional, as you saw in that last slide. Energy costs are low and joints are flexible. Versus the classical mechanical, the stress strain curves are linear, local for their stress distribution. Structural distribution is discontinuous. They're gravity dependent, as our lever examples show. They are unidirectional. Again, my elbow moves in multiple planes of movement, not just in the sagittal. And then their energy costs have high energy and they're rigid, fixed joint motions. But these don't apply to our biological systems. Our tensegrity model is more in line with each of the means by which the biological system actually adapts and has these mechanical properties. Okay, so if we're in agreement, thanks for agreeing, right, that we are biotensegrity models. Then if we look at what I've tried to do is we'll start macro scale and then go micro scale. So at a regional level, we have our myofascial slings. On our intramuscular, we have connective tissue that connects not only the myofibrils, but the adjacent muscles themselves. Within the muscle, we have interconnective tissue where I use the example of a biceps, if we stick with that, right? My bicep is a funny mouth noise that I make to describe a whole compilation of over 10 million different muscles within that. Because depending on the muscle, we'll talk about like the supraspinatus, that 30% of the muscle fibers within your supraspinatus tendon, they don't go end to end. right? They actually terminate within the muscle themselves, suggesting that there's actually micro tendons within that muscle. Your deltoid, depending on the cadaver and the morphology, over 70 to 80% of those muscle fibers actually terminate within the muscle themselves. Again, suggesting that your deltoid is multiple muscles simultaneously. And people talk about the all-in-none principle when you actually fire a motor unit. A motor unit, you're correct that all the muscle fibers within a motor unit actually fire together, but that doesn't mean that if I go like this, that my entire deltoid lights up. No, a very small percentage of a small subset of my motor unit pool actually fires in order to create the motion that I'm describing. Then we will go a little bit intracellularly briefly and intracellularly down to again trying to boil it, get down to the root cause of how we actually produce these forces. If you haven't seen this YouTube video, I think it's probably one of the better videos that I can use to convey my mental model and imagery of how this tensegrity model actually works. And what you're looking at is the dermis, the epidermis, the connective tissue of fascial. They call it, the terminology, if you want to look at it later, is called scrolling under the skin. And you actually look at how this fascial tissue that I schlepped off within my DPT curriculum in the cadaver dissection is actually incredibly important as far as like how we actually transmit force across this biotensegrity structure, which is the human anatomy. So again, thinking about the linear model and somewhat of a reductionist approach, you can see it listed across the top. So my muscle contracts, it transmits this to the musculotendinous junction, to the tendon, then to the capsule and the labrum, the connective tissue, the enthesis, and then into the bone or cartilage. But really, the force does not go linear like that. In fact, I'll convey in the coming slides is that there's also radial forces. When said muscle contracts, it doesn't just go along the muscle belly, but it goes in all three different directions. They call it radial forces, not just axial forces along what is the pennation angle of the aligned myofibrils. Additionally, what I've really been fascinated is even this affects not just, again, as I alluded to, the musculoskeletal system, but even our neurovascular bundle. It can be a conduit by which we transmit these myofascial forces and allow for adaptation to occur. So if we zoom in to our sorry, that went a little bit quick. Oops. All right, so we have our stratified gradient here, which is what I would say is a little bit more of a reductionist. And then we have more of our continuous gradient on the right-hand portion of the screen. Now, without the labels that I put in there of tendon and unmineralized fibrocartilage, etc., it may be quite difficult. I would have difficulty determining where the tendon ends, where the muscle begins, and where the bone begins, right? And the reality of the situation is that these tide marks are not like lines in the sand. They are interdigitated continuity of biotissue and structure that allows for this gradient of forces that you guys are applying in clinic on a daily basis to not only just adapt the muscle, but adapt the fibrocartilage, the enthesis, the tendon, and every structure there within. I just spoke about the intramuscular skeletal tissue. So what you're looking at is a zoomed in, crystallized version of the paramecium, which has this kind of honeycomb shape, which has these small little orange things that look, you can see it up here, right? They're called integrins. That's how when the myofibrils contract and change, not only their circumference, but also in their contractile properties, those integrins then transmits the force into the basement membrane of the connective tissue and transmits the force, as I mentioned, more laterally. A great image of that is shown on this coming slide. And I use, the purpose of this slide is just to reorient us to what is the epimysium, the paramysium, that it actually, like these things that we, at least I hadn't historically thought about this on a regular basis in clinical practice, but it has got this paradigm shift has got me thinking about it on a more frequent basis, and I'm hopeful that as we go through this weekend's course material, that we're thinking about how some of the interventions that JC shows you is not only just affecting said muscle, but acting as an actuator of that muscle to affect the connective tissue there within. Here's my visual of the radial forces. So you have the resting muscle unit to the right, and then we have the contractile unit in the middle there, and then you can see 1, 2, and 3, which are relatively small numbers. Sorry for if you have to squint, but hopefully it's bigger on your screens. Of ways in which the contraction of the muscle induces things other than just longitudinal forces of how we actually think of it. And the graphical representation, I'm big on graphs. I don't know, it just helps me to conceptualize these concepts and others. If you're not as familiar, or you like more of the picture format, let me describe the graph for you. So on the y-axis you have your newtons or force, and then on the x-axis you have your sarcomere length. So you're looking from a contracted, the smaller the sarcomere, the more the contracted the muscle. So on where it says 1.5, you have smaller sarcomeres, and then if you stretch it out, etc. But what you're seeing is the mapped forces of radial and axial forces. So axial forces are going along the muscle belly, and then your radial forces are up to 2.4 times as much as what is actually going along the longitudinal. What does that mean? It means like when I do a bicep curl and I do, I don't know, 10 pounds of force, for instance, we'll use that as an example, I'm actually getting up to 2 to 3 times more force adjacent and perpendicular to the line of contraction, which is, again, for me was really interesting. And again, it's not only, it again takes what was a simple mental model of the human body and has made it a little bit more adaptable and allows me to be a little bit more creative within my clinical practice. Okay, so let's talk about, so that you transmit that force radially, and then where does it go? It goes into the connective tissue. I gave you that example, but then on a cellular level, it actually stresses the cellular membrane, and then you have, we hear about actin and myosin filaments, and we think about muscle, but these actin myofilaments act not only as a structure for the cell, but they're actually within the cell. They give the cytoskeleton its structure there within. And what you're looking at and watching is a cascade of how how the forces that you induce or ask someone to do through their exercise transmits the force down through the cytoskeleton into the DNA and determines the protein synthesis that then would otherwise come. And again, for me, it was like super empowering. And I think I watched this video and I drift back to my conversation with my mentor and friend, and I'm like, well I'm making some effect, right? Whether that's important or not, or whether that helps our regression to the mean, but every time that we induce an exercise, or passive or active or otherwise, we are going through this kind of cellular cascade, and we are really empowering other people to be their own mechanical force transmission. I think of more of like a conductor of an orchestra of sorts, where they are really empowered to be able to learn what the rules are of like what is the rate, the frequency, the intensity of the forces that they apply to otherwise determine the epigenetic effect and thus the structural changes that they undergo. Okay, so we started high level. I went through each of those cascades, and this was the purpose of this is to say that we know what mechanical transduction and mechanical therapy is. I tried to walk us down through the DNA all the way up through the cascade, through like myofascial force transmission, or the myofascial slings. and how that force transmits across each of the hierarchical levels that you see here. So what, right? So what are the implications of this? Practical implications, let's talk about that. So mechanical forces influence the growth, shape, and determine the behavior of nearly every cell, tissue, and organ in the human body. Externally, that means the weight that again, thinking through analogies, the weight that I give someone to do an exercise externally versus internally, the force of their muscle contraction, the intensity at which that is done, provides mechanical stimulus that can be used to facilitate adaptation and accelerate healing and promote optimal tissue, facilitate adaptation and promote optimal mechanical properties, load-bearing capacities, and thus both contractile and non-contractile tissues there within adapt. Again, we use the muscle as actuators, but they're not the sole means by which we enhance the system's biological capacities. Modern science of biological tissue mechanisms is best explained through these biotensegrity models, as I mentioned, and the cross-linking on multiple levels and hierarchies through radial and linear forces. So the biotensegrity concept is one of the main takeaways that I want you to get out of this subsection. It's based on the fundamental rules of physics, may represent a paradigm shift in the way that rehabilitation professionals think about the human body, and part of the basic science that underpins clinical reasoning. Human biological systems no longer need to be thought of as bones, muscles, and fascia as in isolation, but they are intertwined as a whole body kinematic system. Locopathological alterations of mechanical tissue properties are projected to neighboring and remote regions through that scrolling under the skin type model that I described as causing non-local symptoms, right? This is kind of the principle at hand would be your regional interdependence, right? I can affect the shoulder by loading the elbow, for instance. And then treatment interventions targeting local and non-local to the site of the injury can promote adaptation, healing, and enhance physical function and performance, leading to superior clinical outcomes. So I said that I was going to talk about three main concepts. That was like our mechanical transduction and our biotensegrity model. We're going to now talk about the mechanisms, the law of thermodynamics and biological adaptations.